It is my pleasure to make a presentation at the MetComNet 2020 conference on communication networking and traffic management for autonomous transportation systems. I am Professor Izhak Rubin of the Electrical and Computer Engineering Department at UCLA. I'll divide my presentation into two main parts. In the first part, I'll talk about traffic management mechanisms. And in the second part, I'll discuss data networking algorithms and protocols. At the end, I'll briefly discuss the interplays between the performance metrics involving data communication networking and vehicle traffic flows. Results presented here are from joint studies and investigations with Professor Andrea Baiocchi at the Sapienza University of Rome in Italy, Dr. Julia Sagnotto, a PhD student of mine who just graduated at UCLA, and Professor Ion Turkano, who are now at the University of Luxembourg. See also the references for other joint investigations. I'll start by talking about traffic management for autonomous highway systems. The models that I am going to focus here on are presented in the paper noted below. So we have a multi-lane highway with autonomous vehicle flowing on the highway in multiple lanes in both directions, even though I show here a single direction. As you see here, I have arranged the vehicles in platoons. So here is a platoon of vehicle, and here is another platoon, and here is another platoon of vehicle. In each lane, you see a platoon, and you identify a platoon leader as well as a platoon trailer. We also note access network here and dissemination of messages from a vehicle over a specified span. To model the traffic management system, consider a segment of the highway that consists of multiple links. In this sample, you see link 1, link 2, link 3. Each link is attached to incoming ramps and outgoing ramps. Even though I show an incoming ramp here and an outgoing there, actually it's dual at each point. So vehicle arrive to the link, they queue on ramp, they are admitted into the link in accordance with the admission mechanism, they are arranged in platoons, and then they flow across the link at specified speeds and with specified inter-vehicular distances. So here I show the platoon formation. In this example, there is a single lane, vehicles are arranged in platoons, and you can see in each platoon multiple vehicles. dV is the distance between vehicles which are members of a single platoon, and dP identify the distance between platoons. S is the span of a single vehicle. So if you look at this as a platoon, you see the platoon leader and a platoon trailer. Other parameters in my model: the length of a highway link, L, lambda, the vehicular arrival rate at an entry point. The arrival process can be a cross-on process. Mu is the effective service rate provided by the highway to arriving vehicles on the on-ramp. It's defined as the mean rate at which vehicles entering the link from its input lane are admitted into the highway, in joining existing platoons or forming new ones. Do note that many of the results I'm presenting do not depend on organizing vehicles on the highway into platoon formations, but I will keep this structure for my discussion. Additional platoon formation parameters. DPL is the distance between two successive platoon leaders. DV, as I already indicated, the minimum distance between vehicles that are members of the same platoon. And DP is the minimum distance between platoons. I model DP as equal to DV plus G, and G represents an access gap range beyond DV. I synthesize G to account for the need for gaps between platoons to accommodate the transition of vehicles between lanes, vehicles arriving or departing from the highway, as well as vehicles that change lanes. Additional parameters. N is the number of vehicles in a platoon. V is the speed of a vehicle in a platoon. Other parameters I'll define later, but U is to be noted is the nominal deceleration of a vehicle. That means if a vehicle needs to suddenly stop, what is the deceleration rate? Very important is to note that DV, the minimum distance between vehicles in a platoon, is proportional to V squared over 2U, the speed of the vehicle to the second power, divided by twice the deceleration rate. Multiply by a factor zeta, which accounts for the range of dispersion of the acceleration factors. So DPL, the distances between the platoon, can be expressed as the sum of these underlying parameters. Accordingly, I note the maximum serving rate of the highway link realized when every platoon is available to admit into the highway n vehicles is given by mu equal to n divided by dpl over v. That means if I can admit each time a platoon arrives at an access point n vehicles, the full capacity of a platoon, or a subset of it, as we'll see later, but assume for now the full capacity of the platoon, noting that the time between platoon arrivals at an access point is dpl over v, then the admission rate and therefore the serving rate of the highway is given by that formula. Using the expression for dpl that I noted before, we get the underlying equation for mu. Do note the dependence of mu on v, on the speed of a vehicle. You have v in the numerator and v squared in the denominator. So what does that mean? It implies that the serving rate grows with v initially, and then it gradually decreases as v increases due to the decreased density induced by the requirement of maintaining safety spacing ranges between adjacent vehicles. And in fact, noting the transportation equation, we observe that under equilibrium condition, the mean flow rate F is equal to the product of the mean density nu and the mean velocity v. Consequently, as we increase the speed of a vehicle initially, F increases, But eventually, as we increase the speed of the vehicle, and we have to keep vehicles apart from each other, the density of vehicles on the highway decreases, and the product yielding F starts to decrease. So if we express, consequently, mu v as a function of v, we can note that to maximize the serving rate, mu v, we can calculate the value of the speed that needs to be chosen. And it's given right here as v star, and the maximum service rate is given right here. In the model, I set the gap, the parameter that identifies an excess gap between platoons, to be equal to psi dv, where psi is larger or equal to 1. That means as I increase psi, I increase the gap to allow for more transitions of vehicles between platoons. If you look at this result, you can calculate what should be the speed of vehicles across a link in order to maximize the serving rate, and I give you here an example. However, of more interest for our study here is to find the maximum throughput rate, F, that can be accommodated across the link under delay constraints. We are setting here the following model. We account for both the incurred on-ramp excess delay and the highway transit time. So if you look at this equation, you see modeling the queue of vehicles waiting for admission across an incoming ramp as an MM1 queuing system. The expression here tells you about the average delay of a vehicle on ramp prior to admission. The second expression, L over V, is the transit time across the link, whereby the vehicle has to cross a distance of L at a speed of V. So the sum of the two is the total delay incurred by a vehicle in waiting on ramp for admission plus in transit. I set an upper bound on that by defining D naught as a sum of two components. D naught Q is a targeted upper bound on the queuing delay to be incurred by a vehicle waiting to be admitted into the system. And L over V target is an upper bound on the transit time across a link of length L. In fact, what I'm interested in doing is synthesizing the system in such a manner that the sum of the two is attained. Looking at the formula then for mu v and extracting the parameter lambda out of it, we immediately see that lambda is upper bounded by this expression. So in order to meet the underlying delay constraints, queuing delays plus transit delay, the arrival rate and subsequently admitted rate is upper bounded by this expression. This upper bound is noted here by the function f. So how do I synthesize the system to achieve the highest throughput rate under this delay constraint? I give you here an example. Let's take a look at the results of this example. What you see here is the optimal velocity as a function of the link length for a certain set of parameters in terms of the on-ramp queuing delay and in terms of the transit time to be experienced. This is actually the transit speed target value. As you see here, n is a parameter, but the optimal speed does not depend in a significant fashion on the number of vehicles n in a platoon. As the link length is longer, we will set the vehicles to proceed at a higher speed in order to meet the transit time objective. And that's quite interesting to know. This is the optimal speed, as indicated here, for each value of a highway link. In turn, if we calculate the optimal vehicular throughput rate across the different links of different lengths, we see that the highest efficiency, highest throughput efficiency, is obviously when the number of vehicles in a platoon is high, because then the overhead of the distances between platoon is not as large. And we also see that the optimal vehicular throughput rate does not vary in a significant fashion over the link as a function of the length of the link, even though the optimal speed does vary, as we've seen before. And we can see that we can achieve a significant value for a very high vehicular throughput rate if we appropriately optimize the synthesis of the system. Now I'm going to extend this model. We talked about a single link. Now what if we have a multiple link topology? Let's say first with each link consisting of a single lane. For this purpose, assume that we have F as a set of vehicular end-to-end flows accessing the highway. L is the set of highway link. Lambda S is the mean vehicular arrival rate of external vehicle flows for flow S. If we sum the arrival rate of all the flows, we get the total arrival rate, lambda. What we observe here is we consider the flow of each type, and for each flow, a certain links are members of the underlying route, as indicated here. The mean rate of vehicles entering the highway through a ramp of link K is nu K, and summation of nu K is lambda. Phi K is the vehicular flow in the case highway link, also referred to as the internal flow. So externally, vehicles arrive at rate nu K to link K, and after we navigate them internally, the flow rate at each link K is denoted as phi K. Assume a Markovian transition matrix from link to link. So the probability PHK that a vehicle having completed its transit through highway link H will move to highway link K is PHK. The summation of PHK over K can be less than 1, as a vehicle can leave the highway after having traveled on link H. As we do for queuing networks, we can calculate phi K by solving the set of coupled equation shown here. So given nu K and given the Markovian transition matrix, we readily calculate phi K, the flow rate at each link K. So having such a network of links, let's look at a model that we have studied for synthesizing the system. What we do here, we look at each individual link K and we calculate the mean queue size or system size of vehicles waiting for access across the access ramp, which you see right here, and we add to it the mean queue size or system size of vehicles flowing across link K, transiting link K. Note that phi K is the rate of vehicles in lengths in link K, and note that I am using Little's law to express the mean queue size as a product of the underlying rate and the mean delay. Looking at this expression, which is the sum of the queue size of vehicles on the input ramp and in transiting link K, I am upper bounding it by taking into consideration the target delay for queuing on ramp, DOK, and multiplying by the flow of vehicles through the input ramp, and by the target transit delay across link K, LK over V target, and multiplying that by the flow rate across link K in accordance with Little's formula. So I get a constraint here that takes into consideration the underlying delay objectives. I can manipulate algebraically this expression, whereby I divide both sides by nu k and define xk as phi k over nu k to obtain this inequality, which basically, if you look at it very carefully, is pretty much the same as we got for the previous case. Accordingly, we can go ahead and write this set of linear equation for the calculation of xk, which is phi k over nu k. Obviously, nu k is given, so basically we calculated before phi k, and we can write this expression to calculate the ratio xk. So that's readily calculated to start with. It depends on the distribution of loading on the system and the underlying route undertaken by each flow. To optimize the synthesis of the system, the traffic management system, we assume a route-dependent payoff function, LS, which is defined right here, whereby, for example, we can use a weight qk on link k, which can be proportional to the length of the link, or can assume some other cost functions. The overall objective function f, accordingly, would be some weighted sum of the flows over the different links. Qk could be proportional to Lk, for example. So the optimization problem in managing the traffic across this autonomous transportation system would be to maximize this objective function, f over phi k, such that this bound is preserved, and this bound has to do with meeting the delay objectives that I indicated to you before. This upper bound induces delay constraint shown here on the flow on each one of the links k, as indicated right here. And f is basically the same f function I defined before. So, in essence, I have to calculate the value of nu k, the arrival rate at link k, that maximizes this function, times the weight. The weight could be proportional to Lk. Let's consider then an expanded system whereby I still have a multi-link topology, but instead of a single lane, I have multiple lanes across each link. Well, if this is the case, let's phi k denote the flow rate across link k, lane I. And I get this bound on the total queue size as indicated before, relating to the delay to be incurred by vehicles that are admitted into link K and routed to lane I in link K. Do observe that I have chosen here to have different target speed for different lanes. So for example, I can dedicate certain lane to be fast lane with a higher target speed and others to be slower lane. So the corresponding bound is as follows. Assume that I look at the flow phi k at link K and assume I do the following. I also look at the incoming flow rate nu k, and I allocate vehicles that arrive at link K to lane I with probability Rik. So across the input ramp, let's say I have multiple queues. The vehicles are queued in multiple locations depending on the lanes that I am targeting them to go to. And a fraction Rik of the vehicle arriving at link K will be targeted to go to lane I. Similar, I will set phi k to be Rik phi k. Accordingly, the upper bound indicated before is now applied to each lane of each link as indicated here. If I look at this bound, this is algebraically mapped into an upper bound on phi k as indicated right here. And I can see that this upper bound can be achieved by setting Rik to this ratio here. Everything here can be calculated as shown in the equation noted above. So this is the optimal routing of vehicles to lane I across link K that will result in maximizing the flow across the link. Next, I would set the system in such a way that I meet an objective function f defined similarly to the way I defined it before, with weight qik that can depend on the underlying link I. So based on this setup, we can go ahead and compute first the fraction xk, as I have done before, based on the routing probabilities and the distribution of flows across the transportation network. Set the lane and link velocity level to values that maximize this function f, and then calculate Ri in this fashion, and then go ahead and calculate the objective function. And in fact, to get more detail, you can see the exposition in our reference paper. We ran an example of a ring highway around Rome, Italy, and we observe accordingly the following design. You have lanes 1, 2, and 3. Lane 3 is a faster lane than the other ones, with a targeted lower mean delay. And interestingly enough, we can see that the vehicular throughput rate achieved across each one of the lanes in particular if there is a sufficient number of vehicles in each platoon, is quite high and about the same. Which basically means in the fast lane, we keep vehicles away from each other and they move at a higher speed, but the product of the two gives you a flow rate which is about the same as a flow rate that we get at a slow lane, whereby the vehicles are flowing closer to each other at a lower speed, but the product of the lower density, the higher density actually, and the lower speed gives you a flow rate which is about the same. Interesting. Second part of the presentation, I'll talk about data networking for autonomous highway system. So the model that I'm going to talk about here very briefly relates to dissemination to highway vehicle within a targeted span. So a vehicle moving across the highway have messages that it wishes to disseminate, multicast to vehicles within a certain range from itself. Messages can be critical messages or low priority messages. The critical messages are such that they have strict low latency requirement, and the low priority messages do have delay requirement, but they may be produced at a much higher rate. If you look at requirement to support variety of message classes in an autonomous system, you can see in fact that depending on the message type, there are specifications of the communication range, like a message of a certain type issued by a vehicle needs to be communicated over 250 meters, over 1,000 meters, or other ranges. These are the dissemination range, and they do have maximum end-to-end latency and reliability numbers. And that's what we intend to satisfy. So our objectives in the studies of data networking, which I'll very briefly indicate to you, are such that we like to maximize the aggregate data throughput, assuming a packet delay which is lower than a specified maximum packet delay over 95% of the time, and assuring that the probabilities that the packet is successfully delivered to all vehicles within the dissemination span, the packet delivery ratio is high, 90% or so. For that purpose, we developed networking mechanism and determined joint configuration and parameter settings across the physical layer, selecting modulation coding scheme, data rates, interference mitigation schemes, and transmit power levels. The MEC layer, looking at variety of scheduling mechanism. I'll concentrate here on FDMA-TDMA, but may be briefly mention 802.11p, but mostly FDMA-TDMA mechanism. And at the network layer, looking at V2V routes, RSU-based routing, and others. So let's start with vehicle-to-vehicle data networking on the sub-6 gigahertz band. So what you can see here is that we have multiple vehicles that flow across multiple lanes on the highway. I arrange them in platoons. And according to the algorithm that I am talking about in this section, we are using mechanisms that I developed several years ago, which I called a vehicular MBN mechanism, vehicular mobile backbone network mechanism. In each cell, consisting of multiple platoons, I select one vehicle to act as a backbone node. Within an access network, all other vehicles that wishing to disseminate messages across the highway communicate to the backbone node. The backbone node form a BNet, a backbone network, and communicate the messages across the backbone network from one backbone node to another backbone node to another backbone node. In each cell, each backbone node will broadcast the messages to all members of the cell. So this is an hierarchical solution that consists of A nets, access nets, and a B net, and a backbone network. Everything is moving, so everything is fluctuating. And there is a dynamic selection or elections of backbone nodes and of A nets. And we worked on the design of such a system. And without getting to the detail, you can look at the references. You can see here an example of the throughput efficiency of such a system as a function of the distances between backbone nodes. And what you see here is that operating at a certain data rate and modulation coding scheme, let's say the black curve is at 24 megabits per second, as the distances between backbone nodes increase, obviously, the throughput efficiency will decrease, but in a highly nonlinear fashion. So we can determine accordingly what would be the throughput efficiency of the system depending on the underlying loading of the system, density of vehicles across the network. And we also note that simultaneously, to mitigate interference, we have parameters such as K and M, which indicate what should be the spatial reuse factor within the backbone network and what should be the spatial reuse factor in mitigating interference between transmissions in neighboring cells. So that's all optimized simultaneously. This is for a TDMA, ANET, and BNet operation, and we have done the same when we use other MAC algorithms. Second model, assuming infrastructure-aided networking for autonomous vehicle system on the sub-6 gigahertz band. I'll give you some references of papers to get more details. What we see here is the following. Now I am assuming that I have an infrastructure system consisting of roadside units that are interconnected via a backbone network. Let's say interconnected via fiber links, and they can intercommunicate at very high rate. Each roadside unit is managing an RSU cell, as you see right here. So the communication here is indicated whereby a source vehicle will communicate V2I to its associated RSU. The RSU will communicate to other RSUs across the backbone network. And upon receiving the disseminated messages across the backbone, the RSUs will broadcast the messages in the other cells. So this is basically the flow of information as indicated right here. Information is flowing V to I, backbone, and I to V accordingly. To optimally design the system by setting the cross-layer parameters, we have to select all of these parameters shown here for the purpose of maximizing the throughput rate under some delay constraint. And we have done so. And this is some examples of parameters to illustrate performance, and I won't go into that. And we assume variety of medium access control algorithm, but let me focus on the TDMA or FDMA mechanism. And we can see results such as those illustrated here. The total throughput of the network is shown here as a function of the distance between RSU nodes. Of interest here is to see how the throughput efficiency of the system behave as the density of the backbone changes. It gets more and more expensive to install RSU nodes closer and closer to each other. So as the distance between RSU nodes increases, obviously the throughput efficiency will go down, but the question is by how much? And this is well illustrated here. So we get high throughput efficiency if we set the distances between RSU at 100 meters, And as we increase the distances between RSU to 300 meters and beyond, the throughput efficiency goes down. If the distances between RSUs is beyond a certain threshold, as you see right here, we have to change the modulation coding scheme and decrease the underlying link data rate from initially a value of 24 megabits per second to a value of 12 megabits per second. And those are the transitions shown here. This indicates what would be the optimal setup for 802.11 mechanism. And this provides an example that illustrates the differences between the operation of a demand-assigned TDMA, that of 802.11p, whereby the demand-assigned TDMA is much more efficient, as one would expect. We also see here a comparison between the throughput efficiency of the infrastructure-aided system, the blue curve, the V2I system, versus the black curve, whereby you have a pure V2V mechanism, such as the one that I discussed earlier. And the infrastructure-aided mechanism provides a significantly better throughput performance, provided, however, as you see here, that the backbone is dense enough, which is quite interesting. Finally, the third model for networking that I'll briefly discuss here involve millimeter wave data networking for autonomous vehicle systems. And I'll refer you to our paper in this conference, in the 2020 MedComNet conference, and the presentation by Dr. Yulia Sanyoto and myself, whereby you get details of this model. But I'll say a few words about it. So we have here an RSU infrastructure-aided millimeter wave multicast dissemination algorithm, which is the RSU-aided millimeter wave dissemination algorithm, the RAMDA algorithm. And for comparison purposes, I also have a basic V2V millimeter wave multicast algorithm. Now, basically what I assume here is the following. If you look at the vehicle on the highway, the routing mechanism is such that each vehicle will associate with an RSU, typically the closest RSU to itself, and a gateway vehicle will be selected, a V2I gateway vehicle will be selected in each RSU cell on the highway. And the different vehicles will send via V2V transitions, all directional. Since we're talking about millimeter wave, the communication links are highly directional as it relates to communication links between vehicles in a platoon, as well as the V2I and I2V links. The vehicles will send their messages directionally from one to the other and eventually to the gateway. The gateway will get it to the backbone. The messages will be disseminated across the backbone, and then each RSU will send the messages downlink to the gateway, each gateway in each link, and the gateway will disseminate the messages within each lane on a V2V basis. Typically, we also assume that each vehicle will find a vehicle on another lane which is closest to it and will relay the message to it. So that's pretty much what's happening here. So here are the performance results. This is the delay performance as a function of the throughput rate when we consider basic V2V algorithm, not making use of the infrastructure, that's the red curve. And when we consider the blue curve, RSU-aided algorithm, whereby we have different density level of the RSU. Of course, the most efficient RSU-aided operation is when the distance between RSU node is low, 50 meters, and that gives you the performance here. And in this design, we're typically interested in end-to-end delays that are very low, lower than even 1 millisecond. So if you want to concentrate on the 1 millisecond delay, look at the internal curve here. And what you see here is the following. You see that if you wish to achieve a 1 millisecond delay, you get a higher throughput rate by using an RSU-aided operation than by using a basic V2V operation. That's the red curve. On the other hand, if the infrastructure is not sufficiently dense, the RSU are distant by 500 meters from each other, and you see that performance, you are not going to achieve as good a performance. And in certain ranges, the V2V can give you better performance. And that's quite interesting. Another point to note here is the following. The maximum throughput achieved here, the throughput capacity of the system, is about the same as to whether you use V2V operation only or whether you use RSU-aided operation. Having high priority messages and low priority messages can be nicely accommodated by giving higher priority to the critical messages and setting them in such a manner that they achieve a very low end-to-end delay, as indicated in this performance curve. And then using the rest of the capacity up to the maximum capacity or close enough to it, depending on your delay objective, to support second priority messages. And that's quite interesting. And this is summarized here. Finally, let me make a brief note that when you look at the data throughput performance across the system, and when you look at synthesizing the system to achieve a high vehicular throughput rate, there is a trade-off between the two. In this example, this is done for a VBN-based architecture, but we have other papers that are done for other architectures, and the trade-offs are similar in the following sense. Typically, when you achieve a higher and higher vehicular throughput rate, average number of vehicles per unit time per unit distance supported by the highway is high, the data throughput rate will tend to be low, interestingly enough, because what you see here is that when you achieve a high vehicular throughput rate, basically the density of vehicles is somewhat higher, because in this example, the speeds of the vehicle for each optimization point is about the same. So the density is higher if you look at the average distance between backbone node to the average number of vehicles that are accommodated between backbone node. This is for the first model, for the VBN model. You see the density is higher and the vehicular throughput rate will get higher, but having longer distances between backbone node will reduce the data rate efficiency and the data throughput will go down. In other systems, similar trade-off will occur and have been exhibited by us in other papers, see the references, by noting that when you achieve a higher vehicular throughput rate, for example, by increasing the speed rather than the density as shown here, that would require spacing vehicles farther from each other, and that tend to typically reduce the data throughput rate. And that's quite an interesting trade-off. And by selecting the appropriate desired vehicular throughput rate and appropriate desired data throughput rate, one can achieve a global optimization operation points. Take a look at the different references of our studies, and there are many references of other studies in those references as well. It was a pleasure making this presentation to you. Thank you.